So a unitary operator has the property that the Hermitian conjugate of the operator is its own inverse. And we can show that the time evolution operator is unitary. Now what the time evolution operator does is it takes the state Ej and leaves it as the state Ej, but gives it a phase factor. And of course it does that for all the states Ej. So in other words, that's the time evolution operator, which looks really simple because we've very carefully chosen to put it in the basis of the eigenstates of the Hamiltonian. And if we apply this to its Hermitian conjugate, we just take the complex conjugate of the coefficients, and the Hermitian conjugate of these, we swap their order, but that doesn't change anything. And don't forget to use a different dummy index when you write out it again. And of course, the inner product between Ej and Ek is a delta function. And when we take the sum over that, we're just going to get Ej components. This is going to be 0 because the delta function is going to force these to be the same. So we're going to have exponential of 0, which is 1. So we're just going to have the sum over j of Ej, which is, of course, the identity. So we know that everything in quantum mechanics is described by an element of a Hilbert space, and we know how those elements evolve over time. And the final postulate of quantum mechanics talks about what happens when we make a measurement. How do these elements of Hilbert spaces relate to measurements that we might make in a laboratory? So before we review the measurement postulate, I want you to see if you can remember what happens when you make a measurement on a quantum system.